Hey, Koji.
Hello, can you hear me?
Yes, I can hear you. Can you hear me?
Yes, yes, loud and clear. Long time
Good.
no see.
Yes, I see that you got early as well. So I thought to check the link if it worked, and then I saw
Yeah,
you entering.
yeah, perfect. And then can you share your slides in this case? I will stop my
Yes. I can.
the sharing
Let me
slides.
let me just put it full screen.
Okay, yeah, I can see that.
Is it okay?
Yeah, perfect. Can you move to another slide, for example? Yeah, okay, yeah, it is working. Perfect.
Okay, right.
Yeah,
So
so
I just put the logo here of, do you want me to put anything like, I put here IEEE Foothills section presentation, but that's okay, right?
yeah, of course, of course. Yeah,
I mean,
that is a
I
kind
don't,
of happy part. Yeah.
yeah. Yes, good, good. I
And
was, yeah.
yeah. So, before starting your presentation, let me introduce you.
Mm-hmm.
So yeah, just give me around like a 2 minutes, at the beginning of the webinar. And then I will say like, please go ahead. And then you can start the presentation for around like a 40 minutes or 15 minutes, whatever.
Okay. So it's,
I think,
I
yeah,
assumed it's around 40 to 45. Normally it's
mhm,
around 40 minutes. That's okay, right?
of course, of course. And
Yes.
then we have
Yes.
like a quick, short discussion after your presentation, and that will be great. And then also at the end of the webinar, let me also introduce the next webinar
Mhm.
advertisement. So yeah,
No
please give me
problem.
1 minute for
That's
that
not a
part.
problem.
And usually, we are kind of starving at around 12 p.m. So yeah, if we can
Try not
finish.
to go. Yeah. Yes. Here it's nighttime actually. So it's night. The webinar will start at 9 o'clock at night. So it's my dinner time.
Oh, I see. Did you finish the dinner already or not yet?
No, 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 because if I eat the dinner, then I will not be able to do the presentation.
Oh,
If I eat dinner, then I will be like half sleeping during the presentation, so it's not good. But it's okay. I have I had a snack and I have my coffee, my water, so it's gonna be okay. No,
okay.
no worries.
Yeah, thank you so much for your consideration.
Yeah,
And also, do you plan to join Cigarette Paris session this time?
not physically, but remotely. I will join
Remotely.
remotely. Yes, already Ray sent the invitation, but physically no, because everything was so expensive. And I already went to PSCC in Paris, and it was really, really expensive. And now it's even more expensive because of the Olympics and stuff. So yeah, I
I see.
didn't.
So you mean the expensive means everything, like including accommodation fee,
Yes,
meal
because
fee?
many people go for went for Olympics, and then they stayed to go see the country and everything. So it's very close to the end of the Olympics. And when I tried to find tickets, I mean, a return ticket normally to Paris is around, I don't know, 300, 250 euros. Now it was 600, 700. And then accommodation was really, really expensive. I couldn't find almost anything. So because I'm also the secretary of SIGRE in Cyprus, so I wanted to go because there are some meetings also that have to do with the national committees. But no, it's too expensive for.
But if you are secretary, can't you get any like financial support for your travel to, for example, registration fee or something?
Yeah, for the registration fee, yes, but to be honest, it's a very small section here, and we don't have lots of money because we only started 2 years ago. And so we still are trying to get a little bit like of the finances on track. So I didn't want to use the money for that reason. But
I see.
the president is going, so it's okay. So the president is going because he's presenting something at SIGRE, and he's a convener also for one of the work groups. So he has to go. So there will be someone from the committee.
I see. I see.
Mm.
You know, we had IEEE general meeting 2 weeks ago.
Yep.
And then I met Luis, Pavon Ospina out there. And then we had a kind of talk about our previous secret working group and then also ongoing secret working group like B5, C4, 61. Yeah, so he will join. He will join the Paris session. And yeah, you know, in Seattle, the hotel fee was also ridiculously high. Like I could not find any hotel, the price of which was less than $200 per night.
Yeah,
Wait,
that's yeah.
look, just one person, or maybe, yeah, usually 2 person per room, and then $200 per night. That is, yeah, if we stay at a hotel in downtown area, and I think 300 or 250. So that's too much actually.
Yeah. To be honest, because now I also have a small baby. He's like almost 2 years old now, but still he's like very demanding and everything. I try not to travel very far. So I usually try to go, let's say, one conference every year and maybe one or two other meetings, but I keep them short. So I haven't been to general meeting for many years. Maybe I will try next year. But I was gonna tell you, where do you know Power Systems Computational Conference, the PSCC?
Of course, I know.
Yeah.
Actually, I was a reviewer of PSCC in the past.
Yeah. So we will organize it in Cyprus in 2 years. So it's every 2 years, and this year was in Paris, and I am the chairman, local chair. I will be organizing it here in Limassol, where I live, in 2 years. So
I see.
if you plan to go to a trip to Europe in 2 years, it would be good to keep it in mind. It's a very nice conference. It's a little bit strict because there is always a limit of 240 papers. So that was from the when it was founded until now. They keep the same number of papers. It's 240 papers. But now they're in the past. There used to be, I don't know, maybe 300 or 400 people applying, but now it's something like 1,200 people or 1,300 people applying, but still the number of papers is the same. So it's quite it's a good conference. I think it has a good.
Yeah, of course, of course. Yeah, you know, I was working at Japanese EPRI before, right? And so that time, the Japanese EPRI was also a kind of like a board member of PSCC. I think even now. And then, so my boss assigned, I think 2 or 3 papers for review. And then I reviewed some papers, and then I knew that, so they, yeah, as you said, usually they, how to say, consider a kind of like, yeah, I have to share the screen first.
Yeah, you can put it on the background for
Yeah,
people.
yes. So yeah, let me do this. Where is the picture? Oops. I cannot find the this not this one. Show all windows. It's okay. Good. I think now I can show the screen. Okay, perfect. So if I remember correctly, they intentionally control a kind of acceptance rate. So they try to keep the quality of the conference papers.
Yeah.
So that the review process and then also like a review criteria is how to say somehow more strict than other conferences. That is my
And
kind of impression.
yeah, and also now the all the accepted papers go into a special issue for on EPSR, the journal. So basically,
Oh,
instead of conference proceedings, you get
uh-huh.
a journal publication on at EPSR, which is okay. It's not a transactions, but still it's better than a conference proceeding. So that's very good because when you see it on Google Scholar or on it says like journal EPSR Electric Power Systems Research Journal. So it's a good
Yeah, of course, it is especially good for PhD candidates, I think,
yes
because they need a number of, I mean, kind of required number of journal
journal.
publications.
Mhm.
Yeah, it of course it depends on the universities, but if I remember correctly, especially when I worked at Iowa State University, I heard that once our paper is accepted as a PSCC, and then we can treat that paper as 0.5 journal paper.
Yeah, that's what they told me when I was a PhD student as well.
Oh,
So
okay. Okay. So that is kind of like, yeah, okay.
yeah, it's
Good to
kind
know
of
this.
good.
Yeah. Okay.
Okay.
So anyway, yeah, I cannot join the Paris session as well. So I tried to join it remotely, but because of the time difference, it is not easy to join it.
No,
You know,
it's
yeah, they set from 9 a.m. to 4 or 5 p.m. in Paris time. That corresponds to like a 1
3
a.m.
o'clock. Yeah.
and then 8 a.m. here. So it's not easy to make it. Um,
No. But have you
yeah.
finished with your chapter, everything? Uh,
Um, no, actually not really. So I plan to organize a like this group meeting this weekend, inviting Sergio and then Louis. And then we try to finalize the chapter because, we did not update or we did not organize the meeting for a while. So which means not most, many of the topics can be kind of obsolete, meaning that, so, for example, we briefly mentioned the grid forming converters in conclusion section in the final draft. But when I joined the Algebra General meeting 2 weeks ago, there are so many grid forming converter related sessions. And then
yeah.
I knew that now the grid forming converters are kind of commercially available. Of
Hmm.
course, they are not much installed into many countries, mainly in Australia and then Hawaii Islands in the US. But yeah, anyway, we have to how to say, the kind of drastically update the conclusion section. Otherwise, that chapter 3 is not at all attractive for readers. So that is my the kind of current significant concern. So how we can integrate like a new stuff into the chapter, but I don't think many engineers are passionate to input more. I mean, add more inputs. So
No.
just I try to not to too obsolete. That's
Well,
all.
I have the same problem because the first part of the chapter I'm responsible was about grid codes. And when it was written, everything was draft, and but now I cannot keep it like that because the real ones have been published. So I need to refresh everything and update it again, because otherwise it's going to be obsolete. Yeah. Problem is that the other contributors, many of them are not responding to my emails. So there was a couple of other people, but yeah. Oh,
Is this a guy from Canada?
wait, someone entered now. He's asking when the session will start. It's gonna start in 25 minutes.
Yeah, 25 minutes, yes.
No, the guy from Canada, Nabil, did a review for me, so that was okay. But originally, I was not responsible for this chapter. It was the guy from China, Lei, I think was his name. But then he never
Lading.
responded.
Okay.
Yeah,
I know.
yeah.
Yeah, Lading.
I think he never responded to any of my emails or requests. Originally, I was not supposed to be the responsible for this chapter, but at some point it came on to me. And well, there is a section I asked Ray to check because it's on the protection side, and I have to rewrite the first part that is on the grid codes, because now also there is requirements for generators here. The presentation that Sergio did, they have the 2.0 that they have introduced the new requirements, and also about grid forming as well. And so I would need to rewrite that part because it's obsolete. I think.
Yeah. I have one so I joined the IEEE 2800 technical committees during the general meeting. And then probably you might remember a guy named Jens Bohmer from EPRI. He also, contributed to chapter 6 in our working group in the past. At that time, he was a PhD candidate, and now, he was a researcher at EPRI, and then he was taking a lead to that P2800. That was kind of, the IEEE 1547 is basically for the renewable energy sources that are connected to distribution grid. And then P2800 is basically a regulation for the renewable energies that are connected to sub-transmission and the transmission grids.
Yeah.
And that was finally regulated and published. And then 2800.1 is a kind of regulation, typical regulation like a FRT or something. And then 2800.2 is talking about model validation.
Yes.
And then, so this time, they started to discuss what about considering the requirement that is specific for grid forming converters from now. So that working group has just launched, and then they're gonna cover a kind of like a specific requirement for grid forming converters in the near futures.
Is it something that's still open? People can join. I mean, just as corresponding, right, to see what is going on, or
Yeah, it's a very good question. Usually, anybody can join the technical committee meeting that is held during the general meeting. But
yes,
in
yeah,
order to become a member or corresponding member of that technical committee, that is standards, right? So,
yeah,
uh, yeah. Anyway, the easiest way is to just send an email to Jens Bomer.
okay,
That because yeah,
yeah,
he's still taking a lead to that one, so that would be yeah, the best idea. And then of course sometimes we are asked to become a member of IEEE standards, so which means we have to pay additional money, like
mhm,
$80
yeah,
per year, something like that. So anyway, yeah, I also try to join it and I try to get some information. So if I get something new, and then I can inform you.
yeah.
And also, what is the current status of the grid code in Cyprus?
That was what I was gonna say. That currently we had a big revision last year. That we incorporated a lot of things related to basically it was to bring it up to date to RFG, the European one. And now we are they kind of like outsourced to me, and we're working to build requirements for batteries, but for normal batteries and not grid forming. And
Mm-hmm.
then they want to add requirements for grid forming. And the problem is that there are no standards already for grid forming. Let's say there are some from some preliminary stuff from Great Britain. So they have this kind of like a guideline for grid forming, but it's not a normal standard. And from what I know, there is no standard for grid forming converters yet. That's why I was asking to see if, but yeah, they are a lot in a rush to modernize, let's say, the grid code because there are lots and lots of problems. Problems with fault levels, problems with the short circuit ratio, with frequency response of the system, and yeah, and they're trying to put out fires at this point. It's not a matter of something is going to happen. It's a matter that every day we see these problems, and it's already late. I mean, they should have started 5 years ago to do this work. Yeah.
I see. Oh, so by the way, when I joined the general meeting, do you know Nikos, the very famous professor from Greece?
Yes. Yes.
He gave a presentation about the digital twin in,
Mhm.
I think, Cyprus Island, if I remember correctly. So not Cyprus, probably the different some islands near.
Yes, there is an island in Greece. I don't know if it's Skiathos or something. They have an island that they do that. Yeah.
Yeah, so the idea is that they try to perform the dynamic security assessment regarding frequency stability uh, using digital twins. So they
Mm.
developed the EMT software, and then they collected a kind of system data, and then based on the system data, they get the power flow snapshot and then perform the frequency stability analysis from time to time, and then uh, that results can tell the operator how they can save the system in the case of contingencies. So and then yeah, according to his presentation, it is a kind of, impractical use, and then it is working well. So yeah, just I was so impressed by his presentation. And
Yeah.
then if it is, in practical use, I wanna have more like a detailed information. Yeah, because there are so many small islands in Japan as well. So yeah, that kind of approach might be really promising, I feel. Like
We did something, but not. But I'm always a bit confused when people talk about this digital twin, because for me it's a normal model. I mean, in back in 2017, 2018, we moved the Hydro-Quebec system into a new simulation platform, and it has been in operation since then. So what it does is that every 1 minute it takes a snapshot of the system, and then it initializes and it runs around 1,000 dynamic simulations on a cluster. And then it generates, let's say, some security assessment that updates on the control center. And then after 1 minute, it does the same thing again. So but it was RMS because it's a large system. So EMT was not practical to do that. And we had to prioritize the simulation. So we could only run around 1,000 simulations on the cluster every 1 minute. And we actually did that. And the biggest problem we had was actually moving the model from PSSE to make it work on another software, because the documentation was not very good. And even, for example, for a load model, we couldn't make it match the results for a simple load model connected to a node, and we couldn't make the simulation results match. And we had to get someone to explain to us exactly how they modeled because it was they were doing some tricks inside. So it was, yeah.
Yeah, I think that so we do not have like a generally accepted definition of digital twins, I feel.
Yeah.
Yeah, so what you mentioned was already implemented in Japanese power companies. So we have already established this kind of the control and the protection systems, and that is just treated as one of the emergency control systems that is categorized as like event-based control and protection systems.
Yes.
So yeah, basically, yeah, of course, the manufacturers developed their own like software that is very similar to PSSC. And then so in Japan's case, because there is also a kind of like a benchmark software in Japan that was developed by my previous company, Japanese EPRI. So the power company asked the manufacturers to validate the manufacturer's software, comparing the results between the Japanese EPRI's software's results and then the manufacturer's software's results.
Yeah.
And also, yeah, the load is always a big issue, but especially if the grid size is really big, and then they aggregate large, the amount of loads. So of course we knew that the accuracy of the load model is not good at all. So they pursue a kind of very conservative results all the time. Like if they selected the load model parameters, they intentionally selected the most conservative parameters, which means we try to, if the grid is more unstable, then we can get the more conservative results, right? So
Yeah.
they usually selected the constant impedance characteristics for active power, and so that is a current selection of the Although the actual, the load characteristic is not the pure constant impedance, but they intentionally select it. So anyway, I don't think EMT is not always necessary, but during the general meeting, I also felt that now many countries started to use EMT software even for like a bulk power system analysis. But the problem is that once we perform a single contingency, it takes 1 to 2 hours. Yeah, of course, it depends on the grid size, but if we consider typical bulk power system, and then it takes so long time to get a single results for single contingency. So although we can use like a multiple servers and machines, but yeah, that is not that practical.
Yeah, and it also, not all the software handle this very well. Having multiple licenses, let's say, running multiple simulations at the same time, and yeah. And at the end, you need to be there to get the results and assess and then make changes and run it again. So it's a very inefficient time for the engineer. I mean, imagine running a simulation to check something and then you have to wait 2 hours. By that time, you forget what you are waiting to see. I mean, it's yeah.
Yeah, that's the point. But so in academia, what type of software can we use? Like PSCAD is basically very expensive, right? And then probably academia can use like a free version of
Mhm.
PSCAD. But in this case, there must be a kind of limitation, right?
Yes. Well, to be honest, usually many people just use MATLAB, sim power systems,
Oh.
and because most universities have full license for that. Like our university has a campus license, so many people use that, and it's good enough for prototyping. But if you running small systems like I've run up to the size of the Nordic system. It was not very fast, but also MATLAB has this kind of like acceleration tools where it compiles everything into some sort of executable, and then the simulation is faster. But also we use it's very popular in Europe, Dixieland Power Factory. It also has an EMT version. So, and it's very cheap for academia. So we pay something around 150 euros every year for 25 licenses.
Oh, really?
Yes, while normally for one commercial license is around 10,000 euros, and then another for the first license, and then for the next license it's cheaper. But for us, because it's the university, we pay something 150 euros and we get 25 licenses, and I use it for teaching because it's the same tool that the system operator uses. So I teach this tool to the students because many of them then want to go work to either the distribution or the transmission system operator, and they all use the same tool, this Dixieland Power Factory. And it's the same one used also in UK. So National Grid was using Dixieland Power Factory as well. And in Germany, most of the TSOs use Dixieland Power Factory, like 50 Hertz and Tenet. And I think many of the European countries use Dixieland Power Factory. It's kind of like it's like in the US, I guess it's PSSE. In North America, I think most countries use PSSE, right?
PSSE and PSLF.
Yes.
Yeah, but do we have any limitation of the use of Dixieland if we use it?
There is a limitation but it depends what you get it for. For example, there is a limit. If you take it for only for teaching, then there is a limitation on the number of nodes, not on the toolboxes, but on the number of nodes. And I think it's 100 nodes. So you can run a Nordic system. But if you have a student that is doing like a thesis, then you can ask for a special license and it's unlimited. So, for example, my PhD student, he just sent a small abstracts how he's going to use Dixieland and everything, and they gave him a full license for the duration of his PhD. So that was not a problem.
So for the postdoc, probably they have to buy, right?
Yeah.
Because
Yes.
postdocs are not the PhD students and not a lecturer.
No. The license they gave to my student is called the thesis license. So it's
Thesis, okay.
yes, they give it to master students and PhD students, PhD candidates, let's say.
I see. But anyway, yeah, that's a very good information because yeah, but 100 buses, yeah, the typical IEEE standard model is like a IEEE 118 bus system, right?
Yes. You cannot run that one, no. You can run the Nordic, which is I think around 70 or something, 68, depending which version you use, but not the 118, no.
Yeah, and if we want to add like a more renewable energy sources into the grid system model, and then eventually we need to increase the number of nodes, right?
Yes.
We can easily exceed 100 buses, I think.
Yeah. But if you're looking for RMS type, not EMT, then there is also Dinawo, the one that RT is developing. There is a open source one that is called Dinawo, and I think they also have an RMS, an EMT version, and it's free and it's supported by RT. It's the main person behind it was Patrick Panchaditsi, probably you know him. And now there are other people that have taken over, like Marco and everybody. But it's really strongly supported by RTE, and they answer questions very fast, and it's open source, and it's fairly easy to use. So maybe you might want to look into that.
Okay, can you say the name once again?
Yes, I will write it. I will write it in the chat, maybe.
Okay.
Yep.
Yeah, that is really helpful.
Yes, this one. It's and it's under the Linux Foundation. So it's supported by the Linux Foundation, and there's a lot of support behind it.
I see.
Might want to look into that.
Yeah, this is the first time to hear that. But the Luis also mentioned that nowadays we can use like EMT-based software named based on Julia. Julia is a kind of like Python course. Yeah, then there are lots of like good libraries, and then we can run a kind of power system analysis based on the Julia platform.
They do allow that, but I found it to be very slow, to be honest. I mean, if you plan to run like big systems and multiple analyses and things like that, I found them to be a bit slow. But
I know. Yeah, because this is a typical high-level software, so definitely, the speed is really slow for sure.
Yes, yeah. It's not the same like the specialized software, like yeah.
Okay, good to know this.
Another few minutes.
Yes, yeah, you just take a short rest and then please go back to this Zoom meeting room 3 minutes later. And
Okay.
then, yeah, as you see the screen, I'm going to start in 4 minutes from now.
Okay, good.
Okay. Yeah, thank you. Okay, so let's get started. Good morning, good afternoon, good evening, everyone, depending on the continents. I'm Koji Yamashita, the moderator of this webinar. Welcome to the IEEE PES Foothills section. Our Foothills section covers a wide geographical area stretching from West Covina to the eastern end of California and from Temecula to Baker. Today we have a speaker, Professor Petros Aristidou from Cyprus University of Technology in Cyprus. Welcome to the IEEE Foothills section. Before starting your presentation, let me introduce you. Dr. Petros Aristidou received his diploma from the Department of Electrical and Computer Engineering at National Technical University of Athens, Greece. in 2010 and his PhD from the University of Liège, Belgium, in 2015. During his PhD, Dr. Aristido worked on domain decomposition methods for real-time dynamic security assessment of transmission systems. He then worked as a postdoc researcher at the Power System Laboratory at ETH Zurich, Switzerland, where he developed new control algorithms for future low-inertia power grids. Between 2016 and 2019, Dr. Aristido was a lecturer at the University of Leeds, UK, where he led the Smart Grid Lab. Since January 2020, he has been an assistant professor in sustainable power systems at the Cyprus University of Technology. His expertise lies in power system dynamics, planning, and control. And Dr. Aristido has participated in several working groups like IEEE, SIGRE, CIRED, etc., focusing on the challenges of low inertia systems. Well, Petros, fire away. I will stop sharing my screen.
Thank you very much, Koji. Let me share my screen. Start the presentation. Is it okay? Can you see my slides?
Yes.
Okay.
Let's go ahead.
So, hello everyone. And as Koji said, good morning or good afternoon, depending on where you are. My name is Petros Aristido. I'm from the Cyprus University of Technology, and I'm going to talk a little bit today on different topics. So I'm going to introduce a little bit about what we mean by saying low inertia challenges, and we're going to focus a bit more on frequency stability issues related to low inertia systems, and more specifically on the Cyprus system, which is a small islanded system. So the presentation is split into 4 sections. So first, we're going to do a small introduction on the topic. Then we're going to focus more on the frequency security problems, and then look more specifically in the case of Cyprus. In the last few decades, electric power systems have been undergoing a huge transformation. So we have seen the introduction of large distributed generations in the medium voltage systems, of small distributed generators and energy storage systems in the low voltage systems. We have seen the electrification of transportation. In many countries, governors are subsidizing to get electric vehicles to replace fossil fuel-based ones. We have seen demand response schemes being implemented, either consumers reacting to price signals or to implement some sort of emergency load reduction or peak shaving. We have seen a lot of new smart technologies, which are communication-based technologies to do monitoring, control, and operation, like wide area controllers, or data-driven methods that are being implemented. And in addition to all that, we have seen also the decommissioning of a lot of conventional generators. So either to get rid of nuclear generation or nuclear-based generators, or to get rid of fossil fuel-based generators. And all of these changes are good changes, and especially for us as electrical engineers, is something that is exciting. It's an exciting time to be an electrical engineer. However, for system operators, they have introduced a lot of new challenges. So first of all, we have the loss of traditional dispatchable generation and their accompanying controls, and this leads to new and faster dynamics in the system. We have seen a change in the fault characteristics of the system. And we have seen new control requirements that are introduced. At the same time, due to the intermittent nature of the distributed generation and the new consumption profiles and patterns and the unknown consumer responses, we have seen an increase in uncertainty and new congestion problems that did not exist before. Finally, as power systems are being pushed to operate closer to their limits, for example, distribution systems were never supposed to host, they were never designed to host such big amounts of generation, or they were not designed to host fleets of electric vehicles. We have seen an increase in stability and security problems. So we're going to talk in this presentation about low inertia challenges. But before we go there, let's define what do we mean by a low inertia system. So a low inertia system is a system that has increased penetration of power electronic interface resources and a reduced amount of conventional synchronous generation-based units. And the name of low inertia systems comes from the lack of rotational inertia, which is related to the rotors of synchronous generators. So, for example, we have a shift from traditional power systems where everything was interfaced through synchronous generators into a system where we see everything is interfaced through power electronics. And when we talk about low inertia problems or low inertia challenges, we're talking about the collection of problems that arise when a power system moves from a conventional power system to a low inertia power system. So these problems are not only related to the lack of rotational inertia in the system, but it's a more general term that catches different problems that come from shifting from a conventional system to a low inertia system. In the last few years, there have been an explosion of people working in the area of low inertia systems and trying to understand all the new challenges, understand the new behavior of low inertia power systems. So we have seen a lot of industrial initiatives like SIGRE currently has 3 working groups that work on building some reports for the control, protection, fault levels, monitoring of low inertia systems. We have seen a lot of system operators, especially those in small islanded systems, have been working on understanding what is the impact on their system, moving into power electronic dominated system. ENSOE has also prepared a lot of technical reports in this area. And on the side of academia, there's been thousands. For example, a quick check on Google Scholar shows there have been almost 15,000 publications in the last 3 years. So this is limited to the last 3 years that refer to low inertia electric power systems. And there have been a lot of work trying to understand what are the challenges, how to characterize low inertia power systems, to understand the new stability challenges that we find, to understand the new control requirements that we might have, and even to understand what are the opportunities now that we're moving into low inertia systems. So let's see a little bit what type of challenges we're looking into. So there are, if we look into literature, we are gonna find dozens of different problems and descriptions of things that go wrong when we move from conventional to low inertia power systems. But we're going to look a little bit the main ones and the ones that are more related to the Cypress system, because that's the presentation about. So the first one, and the one that most people are come into their mind when they talk about low inertia systems, is frequency security. Because the lack of conventional generators, meaning synchronous generators, leads to lower inertia in the system and also a reduced primary frequency control. And this leads to an increased rate of change of frequency when we have an event in the system. So we see here, for example, a low inertia system and a high inertia system. with the same loss of in-feed power. And the low inertia system leads to an increased rate of change of frequency and a reduced nadir, a lower dip in the frequency before the system stabilizes. I'm not going to go into more details on this aspect because the second section is dedicated on this. Another big problem that arises is a change in the fault characteristics in the grid, because again, the lack of conventional generators leads to lower fault levels in the system, and then this introduces significant challenges to the protection equipment, relay operation, coordination of the different protection schemes, and it also introduces challenges in the voltage control that might lead to power electronic disconnections when the short circuit ratio is low in the system. We can see the figure on the right-hand side. For example, this is again from the Cyprus system. This is the short circuit level reduction at different substations in Cyprus compared to 2020. So we see that currently there is a maximum fault level reduction of 20% in some substations. And with orange is the forecasted values for 2028, so in 4 years. And we see that it's expected that some substations will have a 40% reduction in their fault levels. So we need to be careful, and we need to make sure that the protections can still operate, and we need to introduce changes into the system. Another challenge is looking into the modeling and simulation requirements when we move into a low inertia system, because most system operators use RMS type models in order to capture, let's say, the dynamics of the system or do time domain studies. But when we have low inertia systems, and especially systems with a low short circuit ratio, this type of models are not accurate anymore, and there is a need to move to EMT type models. This is one example that we can see here. So in the top, we see the simulation on the active power variation of a unit when we have a high short circuit ratio. So that means a strong system. And with blue is the RMS simulation, while red and green are EMT type simulations with different accuracies. And we can see that when the system is strong, while there is a difference in the simulation, at least the overall behavior is captured correctly, and the final, let's say, steady state is captured correctly. While when we move into a low short circuit ratio, meaning a weak system, then we see that the RMS type simulations do not capture correctly all the oscillations that happen into the system or the different interactions that we have. There are many other issues that are related to low inertia systems, like harmonic stability, control stability, and control interactions. That's a very big area. Subsynchronous oscillations that might show up, problems with transient stability or angle stability. Sometimes in low inertia systems, we have problems with damping torque in the system. But we're not going to go into detail into these areas. There is work group, SIGRE work group, that hopefully the final report will be coming out by the end of this year, that discusses in more detail about the different problems and the different solutions of low inertia networks on the protection and control. So in this section, I'm going to go into more detail about the frequency security problems in low inertia systems. So this is the same diagram that I had previously. So I assume that we have a system that operates normally at 50 Hertz because we're in Europe. And then we have a sudden loss of generation here. a fault, which is a loss of generation. So we can see in blue the system behavior. So that's the frequency behavior if we have a low inertia system, and with red, the system behavior if we have a high inertia system. As we said previously, we can see that the rate of change of frequency is much higher when we have a low inertia system, and also the nadir, the dip of the frequency, goes lower. The main security characteristics for this frequency response are the rock-off. So we want the rate of change of frequency, the initial rate of change of frequency, to be limited. Otherwise, it's going to impact the different protection schemes that we might have. It might trigger anti-aliasing protections. It might create problems to synchronous generators that might be connected. We need to limit the nadir, so the dip where the frequency ends up, because otherwise we might have unwanted disconnection of devices, or activating under frequency load shedding schemes, and of course the post-fault steady state frequency that needs to be within a certain bound. The most difficult and most important issue that we have in low inertia systems is the rate of change of frequency and limiting the nadir of the system. How are these characteristics impacted? In the first area here, where we have, let's say, the rate of change of frequency, rock-off, and the nadir, we have interaction. It is significantly impacted by the inertia available in the system and the primary frequency control. Then the post-frequency steady state is only impacted by the primary frequency control, while in this area here we have the secondary control that drives the frequency back to the nominal value. If we talk in terms of reserves, so in terms of products, in the first area here, we have the inertia, which is depends on the generators that we have connected, the synchronous generators, or if we have some sort of grid-forming batteries providing synthetic inertia. And then the primary frequency control in Europe is called the frequency containment reserves. So this is what impacts, let's say, the nadir and the post-fault steady state. And at the end, in many countries, we're now introducing the so-called fast frequency response schemes, which operate again in this area here. So they are very fast response schemes that introduce a certain amount of active power into the system. And the main reason of these is to handle the nadir over here. So if we want to analyze better this behavior of the frequency, in many cases, we use this aggregate frequency response model. If we see it here, we have as an input the power deviation. So for example, if we lose a generator, then this delta PE is a negative value, is a step change. And then we have the generator dynamics here with the damping and the inertia. Then we have the response of the generators. So this is the turbine and governor control. Of course, these are simplified models. And we have the response of the different converters that we have in the system. So for example, converters that provide primary frequency or frequency containment reserves, or converters that provide both virtual inertia and frequency containment reserves. If we put this into a transfer function, we have this function over here that tells us how the frequency will behave if we have a change in active power in the system. And this is the response coming from traditional generators. This is the response coming from droop converters, or converters performing just droop control. And this is converters that provide both synthetic inertia. If we consider only a stepwise disturbance in the electrical power, for example, the disconnection of a generator, then we can replace this delta PE by this here. So delta P is the change, the loss of the power of the generator. And in this analysis, we're going to ignore the converters because at least in Cyprus currently, there are no converter-based generators or devices or resources that provide either frequency containment reserves or virtual inertia. But if we have these sort of resources in the system, then of course we can keep these two components inside. Using this function here, we can go ahead to estimate what is going to be the initial rate of change of frequency, taking the initial response of this function, or we can go and define what is going to be the steady state frequency, so the post-fault steady state of the system, taking the limit of S going to 0, or we can go and find what is the nadir of the frequency, which is the maximum deviation, which is basically where the df dt, so the rate of change of frequency, will become equal to 0. That will give us the minimum of the frequency, or let's say the maximum deviation of the frequency. Now, using this, we can go and compare the required reserves that we need with the limits that we have on the different frequency characteristics. For example, if we check about Rockoff requirements, so we need to limit the rate of change of frequency within some limits. In the Cyprus system, that is 1.5 hertz per second. So using the equation that we found for, we see that the rate of change of frequency only depends on the system kinetic energy. Of course, that's very well known. It comes from the string equation. If we take this function here and we analyze it a little bit, we can compute what is the pre-fault kinetic energy that is required in our system in order to make sure that we're going to keep the rate of change of frequency within the required limit by the grid code. Here we have delta P, so that's the in-feed lost, so that's the generation lost. It could be either, for example, from an HVDC link, or it could be the loss of a large generator. And also here we have this component, which is the kinetic energy that is provided by the in-feed lost. Why this is important? Because sometimes the worst case scenario is not losing the largest in-feed. It could happen that we have a generator that provides a lot of inertia in our system, but at that specific point in time is generating a small amount of power. And that could be a worst case scenario, losing that generator, rather than losing a PV park that is generating more power. So delta P is larger, but does not contribute any kinetic energy into the system. So it's not very straightforward, which is the worst case scenario that we need to use in order to find the kinetic energy required in the system. If we go to the post-fault steady state frequency, again, we can use the equations that we showed before. And we see that it depends only on the available primary regulation. Again, we have here the in-feed loss. So this is the lost power that we consider. And here is the maximum allowed frequency deviation per the grid code. In Cyprus, that's 0.5 hertz. And this depends on the load regulation. So this is the normal regulation, sensitivity of the load towards frequency deviation, and the generator regulation, which this is the frequency containment reserves. Again, using these, we can compute what is the amount of frequency containment reserves that we need in the system in order to comply with the requirements on the post-fault steady state frequency. Again, is the same comment as previously. The largest in-feed loss is not always the worst case scenario. we could lose a generator that does not generate a lot of power, but provides a lot of regulation, a lot of frequency containment reserves, and that could be a worst case scenario rather than losing a higher in-feed power. Also, it should be noted that in most systems, in most islanded systems, there's also the under-frequency load shedding scheme, which provides discrete load regulation. So again, it's some megawatt per hertz, but it's in a stepwise manner. And this is heavily used in islanded systems, especially, for example, in Cyprus. We're going to see later that without the under-frequency load shedding scheme, most of the operating scenarios that we have now in Cyprus would be actually not secure. Now, if we look into the nadir requirements, for example, what is the biggest frequency deviation that we allow in the system? There is a little bit of a problem because the nadir depends both on the inertia and on the frequency containment reserves. So it's not as easy as in the previous two cases because the Rokov depended on the inertia, so we could compute directly. The post-fault steady state relied only on the frequency containment reserves, so we could compute directly, but here it depends on both of them. On top of that, there is a problem that we cannot find an analytical solution that will directly give us the nadir. So it is actually impossible for real systems to do that unless you use numerical methods, meaning using time domain dynamic simulations in order to compute this nadir. If we see the figure here, so we have the system operating at 50 hertz, we have the loss of the generator, and the blue line shows the low inertia system behavior. If we add more inertia into the system, we can see that the Rokov is changing. So we have a lower Rokov, and also the nadir is increased a little bit. So that's the red line. And if we use the frequency containment reserves, so we put more frequency containment reserves, we see that the Rokov remains the same, but the nadir and the post-fault steady state changes. So if we change the inertia, we will also change Rokov. If we change frequency containment reserves, we will also change the post-fault steady state. On the right hand here, we see some scenarios. These come from the Cyprus system. So on the x-axis, we see this is kinetic energy. So these are actual operating conditions taken from the SCADA system. On the x-axis, we see the kinetic energy that was connected to the system at that point. And on the y-axis, we can see the available frequency containment reserves. Then we simulated these scenarios where we tripped the worst case, let's say, generator, and we checked to see if the nadir goes below 49 hertz, which this is the maximum allowed deviation. And with green, we can see that these are cases where the system is secure. And with red, we can see the cases where the system was not secure. Now, the problem is that we can see that in the red area, there are some green dots. And in the green area, there are some red dots. So there is no clear way to say that, okay, if we have a kinetic energy above this amount and a frequency containment reserves above this amount, for sure, we're going to solve the problem or not, because we can see that the red dots are intermingled with the green dots. And some of you might ask, why is that the case? And the case is because the nadir does not depend only on the amount of frequency containment reserves that we have, but also on the activation speed of the generator. So if we have committed generators that, for example, they are gas turbines and they're faster to react, then we might have lower inertia and lower frequency containment reserves, but still be able to be secure in terms of nadir. But if we have slow generators, then even with higher amounts of frequency containment reserves and higher amounts of kinetic energy, we can still be not secure. Now, this is very challenging to try to find what is the best combination of inertia, frequency containment reserves in order to comply with all these requirements and the nadir requirements and be most economical. So in most countries, including Cyprus, system operators have introduced new products, which are named fast frequency response products. And the main purpose of these products is to fix these low nadirs without touching the committed inertia or the frequency containment reserves. There are different solutions in implementing this fast frequency response. In Europe, in many countries, including Cyprus, this is the FFR response scheme that is used. So when a frequency deviation is detected, so there is a trigger frequency, there is a battery that activates, there is an activation time, usually that's around 500 to 800 milliseconds. Then we have a support duration. It provides some amount of active power to the system in order to shift the nadir to a higher value. And then we have a gradual deactivation time here so that the frequency containment reserves can catch this reducing power. If we see here the simulation, again, we have with the blue line is without fast frequency response schemes. So we see that we have a lower nadir, and if we add here 10 megawatt of fast frequency response, then this nadir is pushed upwards. We don't see any difference on the rate of change of frequency because the activation time is not fast enough. So these are not grid-forming units, so they have a slower activation time. So the rate of change of frequency does not change. The post-fault steady state does not change. The required inertia, the required FCR do not change. The only thing that we impact is this nadir here. If we see again different scenarios from the Cyprus system, we can see the first schematic on the left without fast frequency response. We can see here that most of these scenarios are not stable, are not secure. So the nadir goes below 49 hertz. And if we add 10 megawatt of fast frequency response, the same exact scenarios with the same FCR, with the same kinetic energy, half of them become secure. And if we add 20 megawatt of fast frequency response, we see that the majority of them become secure. Just to clarify, the fact that the frequency goes below 49 hertz does not mean that the Cyprus system operator operates the system in an insecure way. It's because there is an under frequency load shedding scheme that triggers at 49 hertz. And in reality, they would shed disconnect some consumers in order to finally stop the frequency deviation. Now, if we go to see a little bit more the Cyprus system, I don't know how many of you know exactly where Cyprus is, because that's a question I get many times when I'm presenting abroad. This is the Mediterranean Sea, and I hope you know where Greece is and where Italy is. So these are countries, European countries in the Mediterranean Sea, and this here is Turkey. And this small island here is Cyprus. So Cyprus is an island in the eastern side of the Mediterranean Sea, and it's part of European Union. If we look a little bit more on the electrical side, we can see that this is an isolated system. So this is an island, so there are no interconnections going to different countries. So this is an islanded system. It operates at 50 hertz, where in Europe has a 132 kV transmission system and around 1.5 gigawatt of installed capacity related to the conventional units. And these are located at 3 areas. So 1, 2, 3 areas. And we have steam turbines, gas turbines, combined cycle gas turbines. in most countries, this would actually be under the category of mini grids. 1.5 gigawatt, if we put it in the terms of the US or any other big country, then most probably they would consider this to be a mini grid. But yes, for us, this is the grid. So this is the national grid for us. So currently there is a peak load of around 1.3 gigawatt, and it has a significant amount of PV penetration. This is in the Mediterranean, there is lots of sun, and currently there are around 700 megawatt installed capacity in PV systems. Around 300 of them are rooftop PVs, and the rest are commercial PVs installed in different areas. You can see here that this is half of the installed capacity of the conventional generators. So there is a significant amount of PV penetration, and there is also wind that I have not included here. At this point, the island heavily depends on under-frequency load shedding schemes in order to maintain the frequency security. If we see a little bit the forecast about installed RES capacity and load demand, these come from the system operator, from the transmission system operator. We're currently somewhere around here at 700 megawatt installed capacity of PVs. And the plan is in the next 6 years to reach around 1 gigawatt of installed PV capacity. At the same time, we see here that the consumption does not increase linearly to the installation of these PVs. And this introduces a lot of problems in the island of Cyprus. First, if we check during low loading conditions, we have lots of problems related to the frequency response of the system. So a lot of frequency security problems, mainly with the nadir. Post-fault nadir, and we're going to see that in the next slide. And at the same time, we have lots of problems with the reduced system strength. This is the same figure I showed at the beginning of the presentation, where we can see that already we have a 20% reduction in fault levels in some substations, and in another 4 years, it's predicted that that would reach up to 40%. But that's not only the case in low loading conditions. Even in medium and high loading conditions, we have lots of problems related to network congestion. So that creates limits in the renewable energy sources hosting capacity. And we also have problems related to the ramp rate requirements of the generators. For example, here we can see different penetration levels. This was taken again from the control center. And we can see that at different penetration levels, we have the ramp rate required by the conventional units to take on the load in the afternoon goes from 20.9 megawatt per hour to 86 megawatt per hour when we reach 35% here. So let's go to see what happens when we have a loss of a generator in the system. So these are 5 scenarios taken from different operating points, going from 0% penetration to 50% penetration. And as expected, we can see that when the renewable penetration increases, then the number of conventional generators connected to the grid decreases. And we have an increase in the maximum rock-off after the fault. So going from 0.4 hertz per second to 0.9 hertz per second. But still, this is within the acceptable limits because we have a limit of 1.5 hertz per second. On the other hand, we can see that the nadir is very bad. We can see that even with 0% renewables, we have a less than 49 hertz of nadir. And when we go to 50% renewables, it goes down to 48.44 hertz. And the only reason that the system survives is due to the under-frequency load shedding scheme, where in the case of 50% renewable penetration, it goes to the 6th stage of under-frequency load shedding, which means that 27% of our consumers have been disconnected in order for the system to survive. How does the system operator handle this? At this moment, what they do is that they enforce the operation of a minimum number of synchronous generators in order to ensure that you have enough inertia and enough frequency containment reserves in order to make sure that situations like this don't happen. But if we have a minimum number of synchronous generators, this translates to a minimum stable generation limit. So this is the minimum amount of power that the conventional units must provide in order to be stable. If we see here different scenarios, so this is a weekday in April where we see the conventional wind PV generation in the system, and the black dotted line, this is the minimum stable generation limit defined by the committed generators. And we see that in certain hours of the day, we need to curtail renewable energy sources in order to comply with this minimum stable generation. And this was in 2023. This is the same day in 2024. We see that the amount of curtailment has increased. And actually, we can see here a little bit in this schematic how this curtailment behaved. And in the worst case scenario, in April, we had to curtail 35% of the renewable generation. So 35% of the renewable generation was curtailed and thrown away, while in 2024, this has reached 40%. Now, how can we change this? Because we don't like it. We don't like to do RES curtailments. The system operator has moved to try to modernize the grid code. So in the last few years, they have introduced a lot of changes in the grid code, and especially changes related to requirements on renewable energy sources and batteries. At the same time, we had a big project in collaboration to our laboratory that we built a better tool that is used in the day ahead in order to better estimate what are the reserves required to maintain the security of the system, and trying to get a better estimate, meaning that we can have a fewer number of synchronous generators connected to the system, which translates to a lower minimum stable generation limit, which transfers to less disconnections. And the other point is to introduce fast frequency response reserves. In the long term, there is a push to move into grid forming, modernize the grid code to incorporate grid forming battery requirements, and also they're looking into interconnections, HVDC interconnections to different countries in order to provide more support and try to stop this renewable energy source curtailment. Now, this is the last part that I'm going to talk. We had a project with the transmission system operator. They asked us to try to provide what are the fast frequency reserves required in order to ensure that the system is secure during different operating conditions. And this was some work from my PhD student, Savas, where we used historical data from the last 4 years, and we selected the number of scenarios that had problems with post-fault nadir. And then this algorithm was used to size the necessary fast frequency reserves needed to fix this problem. So a dynamic security assessment tool was used based on Dixieland power factor time domain model in order to find which of these scenarios had a problem. And then we use the estimator here, which basically what it does is that it does a linear estimation here to try to find what is the amount of fast frequency reserve power that is needed to push the nadir from the simulated value to the target value, which in our case is 49 hertz. But of course, because this is a linear estimation, then this is an iterative algorithm that continues to correct the value until we reach this point. We did that on the Cyprus system, and this was the initial scenarios that we had. The majority of them were not secure, so we had the post-fault nadir below 49 hertz. And after 4 iterations, we ended up fixing all of these problems and estimating the required fast frequency reserves to be 33 megawatt. And a nice result is also that we can see the nadir and the fast frequency reserve have a more or less linear reliance here. So the lower is the nadir, the higher is the fast frequency reserve requirement that we need. This is without under frequency load shedding activation. And if we consider a first stage under frequency load shedding is accepted, so we accept that we can activate the first stage, that is 4% of the consumers disconnected, then running the same analysis ends up that we only need around 19 megawatt of fast frequency reserves. Now, concluding, the penetration of power electronic interface resources is converting traditional power systems into low inertia power systems. And this introduces a lot of opportunities. So we can do many things right, and we can do them better than we used to do them, but also it introduces challenges because it challenges the way that we actually operate the system right now. The impact is higher on small islanded systems, but gradually it will become visible in bigger countries as well. So Cyprus might be one of the first countries that have higher problems, but larger countries are going to meet these problems as well. And for the first time, small countries are forced to be pioneers in this area, because usually countries like Cyprus, they are used to follow what the others are doing. But this time we cannot do that because we're the first ones that actually meet this problem. As a future steps, I believe that, and also the system operator in Cyprus believes that moving into grid forming technologies is a necessity for Cyprus. However, at this moment, there is a lack of standardization and the industrial requirements for these sort of technologies. So although there are a lot of products coming out from different companies, the standardization is not there yet. And also that a lot of the work that we do now should have been done 5 years ago, predicting that now we would be in this situation. So we need to become a bit more proactive rather than reactive, trying to fix things after they've reached this point. So these are my details here, and this is a photo from near my office in Limassol, and I'm going to be a little bit shameless to make an advertisement that in 2 years there's going to be the Power Systems Computational Conference that's going to take place here in Limassol. So if you want to put it on your calendar as a visit to Mediterranean Sea, then you can highlight that it's going to be June of 2026. So thank you very much, and sorry for being delayed a bit.
No, that's perfect. Thank you for the nice presentation and also very informative presentation. Because we have like more than 10 audiences, if you have any questions, and then please type your questions on the chat window, and then the presenter Petros can read it. But before that, some audiences wants to have your slides if available. Can you share your
Yes,
slides with us?
of course.
As a PDF file?
Yeah, I will make a PDF file and send it to you, and you can forward it.
Okay, so in this case, if you want the today's presentation slides, please type your email account on the chat in the chat window. Thank you. Okay, so this time you focused on like the deficiency of frequency response, but you also mentioned that there is a deficiency, the potential deficiency of short circuit ratio, which means the decreasing in fault current level. And then if we increase the amount of renewable energy sources, which part will be more predominant in your system?
In Cyprus, this is a very strange situation because what is happening right now, as I said, there were 3 areas of generation. So it's this area here. I don't know, you can see my mouse, right?
Yes, I can see.
Okay, so there were 3 areas of generation here. And now they are moving into a single point of generation in this area, in Vasilikos area. So the other 2 are being gradually abandoned. And then we have the situation where the fault levels in this area are actually increasing because we're moving all the generation in this area, the synchronous generation, while the remote locations are decreasing. And that's where we saw this like up to 40% reduction in the fault levels. For both cases, for the fault levels and for, let's say, the lack of inertia in the system, now the system operator is investing heavily on going into grid forming technologies. So they're talking with different manufacturers, and we're working into, I'm on the advisory board, and we're working into modernizing the grid code to put requirements for grid forming converters in order then in the next couple of years to introduce grid forming batteries that will also provide fault contribution, to fix the problem of low fault levels, and also to provide inertia and fast frequency response to the system. So they're trying to actually fix both situations using batteries, but the only way to do that is to move towards grid forming technologies.
Thank you. I think we have several questions on chat window. Can you quickly check the chat window?
Yes, they send me two emails, and I see a question. Would you explain why there is an overshoot in the frequency? That's a very nice question, and I was also it was strange for me to see it in the beginning. That's due to the under frequency load shedding. So if you can see here, the under frequency load shedding in the case of 50%, it goes and disconnects 27% of the load because we breach the under frequency load shedding starts at 49 hertz. So that's the first stage. And then every 0.1 hertz, it moves to the next stage. So cumulatively, it goes to 27%, and that's a very big reduction in the load that covers, let's say, the lost generator. And we actually stabilize the post-fault frequency is higher than 50 hertz. And that is the reason. But that's the reality. So that's something that we have seen in recordings of events in the system.
Thank you, Dr. Petros, for your presentation. Very nice. This question from my side. I'm Dr. Khalid from Jordan. Thank you so much. So at 50% and even for 30%, you initiate the under frequency shedding, and you shed the load to compensate the system and help the system.
Yes.
Well,
so actually, currently, in most cases, the Cypress system is not secure if we don't have under-frequency load shedding. So in most cases, during the summer and during spring, especially where we have low loading conditions and high renewables, the under-frequency load shedding is the only reason why the system can maintain security. And this is something that we want to fix, because it happens frequently that it gets tripped and lots of consumers get disconnected, reliability falls, etc.
Okay, thank you.
Problem. I think there is another question. For FFR, it seems that battery is able to improve rock-off. So I tried to, it's again from
yes, I think I miss not. So the battery is not able to provide and improve the rock-off.
No, it's not.
Okay.
It's not, because in this case, for fast frequency response, we don't consider grid forming converters. So usually the response time, as is in the grid code now, it's at 600 milliseconds. And usually the rock-off that we measure, the initial rock-off, let's say, is during the first 500 milliseconds. So by the time that the battery activates and starts providing this support, it does not really affect the rock-off during the initial period. Of course, it affects the rock-off later on, but not during the initial period. If we have grid-forming technologies, which can activate, let's say, in 5 milliseconds or less than 5 milliseconds, then of course, the battery can impact also the rock-off of the system.
So, excuse me, is it like the coming from the nature response of the battery and its converter, or can you comment on that?
These are grid following technologies. So they have a PLL and they measure the frequency, and then they need several cycles to measure the frequency and also to get a good estimation of the rock-off. And then there is the computation time, and then there is the ramp-up time of the units. And let's say these are cheaper technologies, so they are not the same as grid forming technologies. The activation between 500 and 800 milliseconds is considered the standard for these sort of technologies in Europe. Yeah.
Just one more point, please. I have seen something proposing hybrid system, like the supercapacitor and the battery. So supercapacitor is able to help during the rock off, and battery will continue for the primary frequency control. What do you think about this?
That could work. I don't think that's a problem. So the supercapacitor can provide very fast response in the beginning, but again, if you don't move to grid forming technologies that can respond almost instantaneously, again, you will have the measurement issues. So for example, to measure the frequency, usually you need at least 3 cycles, right, to get a good measurement of the frequency, because 1 cycle is not enough to give you an error-free measurement. So usually you need 3 to 5 cycles. And in Europe, that means 60 to 100 milliseconds already to get a measure of the frequency. And if you want to get the measure of the rate of change of frequency, it means that you need to get different measurements and then compute the rate of change of frequency. So already this frequency measurement could take 100 to 200 milliseconds to get a good estimate of the rock-off. So even if you trigger a supercapacitor, you will need to do that after you have done the measurement and after you have gotten a good estimation of the rock-off. So it doesn't, yes, the supercapacitor is faster to connect, is faster to discharge. However, you still have the delay from the measurement and the computation. Maybe there is one.
Great.
Yeah. There is another question from Andy. It says, does the Cypress plan to have 100% capacity of renewable energy? Currently, it's 700 megawatt, and the peak load is 1250. The penetration can go up to 35% in your presentation. Does Cyprus plan to keep raising the penetration of PVs? If that is the direction, the inertia will be lower and lower. Indeed, the plan is to go not to 100%, but as close as possible. So the dream is to go to 100%, of course, like everybody's dreaming about that. However, it's not possible to remove synchronous generators altogether because it's mainly PV and it's geographically very small area. So if there is a cloud, it will cover half the island. So then you lose half of your generation. So it's not possible to go. But in order to handle these, the TSO has two approaches. One is to move to synchronous condensers in order to provide this inertia. So there are some old generators that are being decommissioned, and the plan is to move them into becoming synchronous condensers that can provide fault level, they can provide inertia, and they can also provide voltage control. And the second part is what I said previously, that the grid code is being modernized at this point to allow for grid forming batteries to be connected. And the idea is to have these grid forming batteries provide synthetic inertia and provide frequency support in the system as the synchronous generators get disconnected. I hope I've answered the answer. Yeah.
Yeah, I think time is almost up, but just one quick question. Have you ever considered the headroom of the renewable energy sources for primary frequency response? The headroom. So which we intentionally decrease its output of the renewable energy sources in your study?
Yes and no. It's a complicated question because half of this generation is located on rooftop PVs. And that's the government is pushing more to that direction to have, let's say, smaller PVs on all the rooftops, on all the houses. They give lots of incentives instead of having large generators. And the problem there is that once you have that, now it's 300 megawatt out of 700 is on rooftops. It's very hard to control them because you have like tens of thousands, hundreds of thousands of small PVs. How do you actually control them? If you want to send set points and everything, it becomes very, very difficult. So they prefer to have centralized solutions that like grid forming batteries or synchronous condensers or things like that, that they can actually dispatch and control rather than rely on these hundreds of thousands of small units. But again, that's a preference of the Cyprus TSO. I mean, yeah.
Okay, thank you. Yeah, anyway, so again, the time is up. So the Petros, distinguished power engineer from Cyprus, it was great to have you at the IEEE section webinar today. And everyone, our next two webinars will cover topics regarding grid forming converters, featuring engineers from the US and Spain in September and October. And then the next webinar is scheduled for September 4th, the same time, 11 a.m. Pacific time. And so I will upload the flyer shortly once it is ready. And then please stay tuned and enjoy the rest of the day. And again, Petros, thank you very much for the nice presentation.
Thank you for the invitation, and thank you everyone for listening to me, and have a nice lunch, depending on your time.
Yeah, see you.
Bye.
Bye for now.
Koji?
Yes, I'm here.
Can I save somehow? Yeah, there is a save chat. Okay.
I can also share the the chat log later on. In
no,
this
it's
case,
okay. It's okay. I saved it now, so I have it's to have the emails. So I've saved it. It's okay. Great.
I think you can respond to all of the questions this time, right? Because there are so many like email account and also other messages
Yeah,
on chat windows?
I think. Yeah, the only one was I missed the one of Colin, but I think you asked the question and I.
Yeah, I have already covered.
answered.
Yes.
Yes. The other
Okay,
ones I
good.
think we answered. Okay.
Perfect. Yeah.
Bye.
Anyway, nice meeting you virtually, and then
Yeah.
I will see you in Paris session virtually again.
Yeah.
Yeah. Bye for now.